This video is intended as revision for C3. I've gone through and picked the 10 hardest exam questions in the unit. So these are the questions that I'm going to be covering in today's video. There are two ways you can do this. You can just watch the video straight through, make your notes, use it as a revision, or you can pause on this slide, try and answer the questions, and then mark your work. So each question is going to be worth 6 marks. If you're working a mark per minute, as you're expected to in the exam, I'd expect it to take you about an hour to answer all of these questions. These are hard questions. I have made them deliberately harder than you would get in the exam, because some of you are aiming for absolutely fantastic top grades, and I really want to test you so that we can have the best chance we can for you getting those top grades. In the exam, you might get questions that are similar to this, but chances are they'll be broken down a bit more. I've deliberately made these tricky, I've deliberately made these hard, so that I can test you, so that you can test yourself, see how well you're doing. And if you can answer these, if you can answer any of these in halfway through, you're doing absolutely fantastically. If you get 4 marks on any of these questions, you can be pretty confident that you know the subject really well. If you have a go and you're not sure about the mark scheme that I've given you, pop your answer down in the comments and I'll mark it for you and I'll give you feedback, so hopefully we can make sure that when it comes to the exam you're really confident about these questions. So the first question is working out a titration. Now, every single C3 exam paper I've ever seen has a big maths question on it. It's either about titration calculations or it's about bond enthalpy calculations. Both these subjects are really worth revising. I've made videos on all of these subjects, so if you're a bit confused, go and check out my video, use it as extra revision. So the first thing we need to do is to get the equation for this. In the exam, they will probably give you the equation, but like I said, I'm deliberately making this tricky for you, because if you want to be aiming for those top grades, if you want to be studying chemistry next year, we really need to make this hard for you. So we have a sulfuric acid and sodium hydroxide. Whenever you mix an acid and a base, we're going to get water out of it, and we're going to get sodium sulfate. So we've got our equation. The next thing we need to do is to balance that equation. And the first equation we're going to be using is N equals C times V. So just to remind you, N is the number of moles, C is the concentration, and V is the volume. So I always like to look at questions and then try and work out what we've actually got. So we have 25 centimetres cubed, and there's absolutely no problem with you scribbling all over your exam paper. I definitely recommend you use this technique for chemistry, and definitely recommend you use this with physics, where there's a lot more complicated calculations. So 25 centimetres cubed, this is our volume acid, 0.1 mole, this is our concentration. Acid is titrated against 30 centimetres cubed, that is our volume alkali. So the first thing we can do is work out the number of moles of acid that we have. So N equals C times V. We need to convert the centimetres cubed into decimeters cubed, and to do that we divide by 1,000, so let me just get rid of that. 25 centimetres cubed in decimeters cubed, we divide by 1,000, so that is going to equal 0.025 decimeters cubed. So now we can use our equation, N equals C times V. Our concentration is 0.1 times 0.025, which equals 0.0025 moles of acid. Now, because when we have titration, it has to go to neutralisation, so we know that the Haber ions are going to equal the hydroxide ions. We can use this as our N-alkali. So again, we can say that N equals C times V. Again, we need to convert 30 centimetres cubed into decimeters cubed, which equals 0.03 decimeters cubed. We have N from down here. We can see from the equation that 1 mole of acid reacts with 2 moles of hydroxide. So what we need to do with this number down here is we need to times it by 2. So that means our moles of acid is actually 0.005, which equals C times 0.03. So that C equals 0.005 divided by 0.03. So C equals 0.17. Now I know your calculator is going to say 0.1666666, and some of you might be tempted to write this. Never ever do this. This symbol here, this reoccurring, means absolutely nothing in science. It's absolutely rubbish. Just keep that down for the maths department, and always remember to write your units in. So this question asks for the concentration of sodium hydroxide in grams per decimeter cubed, so we need to do a bit more maths to finish this off. We need to find the mass, the MR of sodium hydroxide. So sodium is 23, plus oxygen, which is 16, plus hydrogen, which is 1, which equals 40, and then we can use our other equation, which is the mass equals the number of moles times the MR. So you might be a bit confused about where our number of moles comes from, but it's just the concentration that we've worked out. So we need the grams per decimeter cubed. So M equals 0.17 times 40, which equals times 0.17, 6.8. So our answer is 6.8 grams per decimeter cubed. So I said this was a 6-mark question. This was an exceptionally long question. So if I just take you back to the beginning, you can have 1 mark for the conversion of centimetres cubed into decimeters cubed, 1 mark for working out the number of moles of acid, 1 mark for recognising we needed to convert hydrogen ions into hydroxide ions, 1 mark for working out the concentration of the alkali. And then your 5th mark is going to be for working out the mass of the sodium hydroxide, and then your final mark is going to be for the answer. So, like with the last question, every exam paper I've seen has a question on titration, whether it's a maths question on titration or whether it's a long question on titration where they ask you about the method. So this is going to be the long 6-mark question, which is going to need your quality of written communication mark in there as well. And your quality of written communication mark is going to come for spellings. So bwette and PhET. Now, anyone that is actually a student of mine will know that my spelling is absolutely appalling, so they will probably find this part of the video quite funny, where I tell you how to spell things. But what I've seen is that you have to be able to spell these 2 words correctly to get your quality of written communication mark. So that is how you spell those two. Hopefully I have got those correct. If you notice I haven't, please feel free to nag me in the comments below. So, describe how to find the concentration of an alkali when using an acid of a known concentration. So, this is going to be my answer here. What I'll do is I'll pause, I'll write it down, and then I'll talk you through it in a second. So, this is my answer here. Prepare 25 centimetres cubed of alkali into a conical flask and add a phenolphthalein indicator. So you can see that I've got my spelling correctly. I've put my alkali into a conical flask and I've added an indicator. That sort of thing that is going to be worth 1, if not 2 marks on the mark scheme. Fill a burette with acid of known concentration. For GCSE, it really doesn't matter whether you put your known or your unknown into the burette or the conical flask. A level does matter, but for GCSE, it doesn't really matter too much. Take the initial reading on the burette and record it. This is really important. While swirling the flask, use the tap to slowly add the acid to the alkali. You're showing a lot of technical skills here, that you can use one hand to swirl and you can use the other hand to control the tap. This is really good stuff. And when the first permanent colour change is seen, this is absolutely key to doing a titration. We are looking for the first permanent colour change, and if you're using a phenolphthalein indicator, it's going to go from pink to clear. Record the final volume in the burette and repeat until the titers are within 0.05 centimetres cubed. Now there's more than 6 marks on here, and I said each question was going to be out of 6. So if you manage to get at least 6 of the points that I've put on here, then you can give yourself 6 marks. There is a lot that you can write for a titration description of the method question, and there's going to be more marks in the mark scheme than is available for the question. But if you write this, then chances are you're going to be hitting every single mark on the mark scheme. So, as I mentioned earlier, there is, a very, very good chance it's going to be a big maths question on your C3 paper, and this is the other possibility for the big maths question, the bond energy or bond enthalpy, which is a bit more of an A-level term that we're going to be using. So the first thing we need to do, and I've been really mean with doing this question, they will, in the C3 exam, give you the equation already, but as I mentioned, I've been mean and I didn't give you the equation. So calculate energy change when methane burns completely in oxygen. So the first thing you need to know is the formula of methane, the formula of oxygen, and the products. When we have complete combustion, the only 2 products we're going to get are going to be carbon dioxide and water. So this word here was really quite key in the question. So that is my balanced equation. The next thing you need to do is to draw all of the bonds we have out. Now, I know some of you think this takes quite a long time, but exams are stressful situations, so I would really, really urge you to spend the time, draw all of the bonds out, and it will be worth it in the end to be confident that you haven't made a silly mistake under stressful situations, because I know you can all do these sort of questions, and I know you can all do simple maths in your head, but these sort of questions are tricky, and exams are very stressful situations. So just take the shortcuts. Use a calculator for doing maths. Draw everything out. Your friends aren't going to know that you did this. Just take the extra time and do things the easy way. So this is how I like my students set up their bond enthalpy calculations. We have the formula up here. We have the pictures, and then what you need to do is to draw a line down the middle, and then we need to list all of the bonds on each side of the equation. So all I've done is pick out all the bonds, and now we're going to count them. So 1, 2, 3, 4 times 4, 1, 2 times 2, OH bonds, 1, 2, 3, 4. Hopefully now you can see why it's valuable to actually draw things out, because 1, 2, it does make things a lot easier when you're actually counting. So now we can refer back to the question, and we can see that carbon-hydrogen bonds are 413 joules, Oxygen-oxygen double bonds are 498 joules. Oxygen-hydrogen bonds are 464 joules. Oxygen-carbon double bonds are 805 joules. So now we just need to employ a bit of calculation. So that's my calculations for each of these, and then we just need to add these two sides together. So that's 1652 plus 996 equals 2648, and then 1856 plus 1610 equals 3466. Now what we need to do is the reactants minus the product, so that's 2648 minus 3466, which equals minus 818 kilojoules per mole, squeezing it in there. And because this is a negative value, we can see this is going to be an exothermic reaction. Now, if in the exam you're a bit confused, you want to like double check whether you've got the answers right. We can see this is an exothermic reaction, and we know that burning stuff is exothermic. Exothermic feels hot, so there in the exam we've given ourselves a little bit of reassurance that we've got the right answer. So I said these were out of 6, so if you manage to get that answer correctly, give yourself 6 marks. I have made this deliberately trickier, so give yourself 1 mark for working out the equation, give yourself your 2nd mark for being able to draw everything. Your 3rd mark is for working out the energy on this side, your 4th mark is for working out the energy on this side. Your 5th mark is the actual number, and then your 6th mark is going to be for adding on your units, because units are so important. So our next question is describing, using diagrams, how a catalyst changes the activation energy of an endothermic reaction. Now it is unusual for an exam question to say using diagrams. There's absolutely no reason why you can't use diagrams to explain what's going on. I particularly like using diagrams. Just because that's the way my mind works. Different people learn different ways, and I'm a very visual learner. So this is my diagram here. We have energy going upside, and we have the reaction going along the bottom. For an endothermic reaction, our reactants are going to be down here, and our products are going to be up here. Now, our uncatalyzed reaction is going to look like this. Uncatalyzed. And our catalyzed reaction is going to have a small hump and look like this. So this bit here, from here to here, is the activation energy, and we can see that with the catalyst our activation energy is lower. So I'll just write this out for you for students that like to have things written out for them, and that's our way of learning. My way of learning is very visual, but it's absolutely fine if you've got a different way of learning to me. So here is written down in words. An endothermic reaction, energy is taken in, it feels cold. The products have more energy than the reactants, so I'll give you a mark for written that, but really I want to be able to see that you can draw the picture for this. A catalyst lowers the activation energy of a reaction, so here we have a smaller hump and a larger hump where the activation energy is smaller. The overall energy change stays the same. So the overall energy change is this bit here, which doesn't change whether you're using catalyst or whether you're not using catalyst. The catalyst just gives a different route for the reaction to take place. It's like taking the long way around or taking the shortcut. You're still going to get there in the same, you're still going to get to the same place, you just might have taken a different route. And the actual distance you'll have travelled as the crow flies is still going to be the same. So those are going to be your marks for this question. This is a very visual question. If I saw this sort of thing come up in an exam, I would expect there to be a graph involved, either interpreting graph or drawing graph. So in this question I want you to compare the periodic table that's developed by Newlands, Mendeleev and the modern periodic table. When you're answering your question, and this is going to be one of the longest 6-mark questions, you need to try and visualise what the mark scheme is going to look like. So here I'm asking you about 3 things. I'm asking you about Newlands, I'm asking you about Mendeleev, and I'm asking you about the modern. So you're not going to get all the marks if you've just told me about Newlands or if you've written me a 2-page essay on Mendeleev, because you haven't hit all of the points in the question. This is a 6-mark question. I've asked you about 3 things. So I'm going to give you 2 marks for each of the different things. If you've written more about that, or I tell you more about that in the answer, I want you to limit yourself to 2 marks per division for this. I don't want you to give yourself more than 2 marks for Newlands, more than 2 marks for Mendeleev, or more than 2 marks for modern periodic table. That's the way the mark schemes are going to look. We need to be a bit smart when we think about how we're going to answer our questions here. So I'm going to pause, I'm going to write down the answer to you, and I'm going to get back to you in just a second. So here's the mark schemes that I've come up with. So Newlands arranged the elements in order of atomic mass. If you wrote that, you can have 1 mark. Elements were in groups that didn't have similar properties. This is a really big problem. For example, he put carbon and titanium together in the same group, and they're very, very different. So he mixed up metals and non-metals, and quite egotistically, he didn't leave any gaps. He assumed that everything that was going to be discovered had been discovered, which ego is a big problem. Mendeleev also arranged things in order of atomic mass, but really importantly, he left gaps, which, he said, okay, future chemists out there, I believe that, you can do better than us and you can discover new things, but importantly, he predicted the properties of what these were going to have. And when gallium and uranium were discovered, he had left gaps for these, and he said, I think these elements are going to be discovered and they're going to have these properties. And he was correct, which is something that was really, really important. The twist in the modern periodic table is that the elements are arranged in order of atomic number. So if you notice that when it goes argon, potassium, calcium, the atomic masses go 40, 39, 40, which is a bit of a difference between Mendeleev and the modern one. But things make a lot more sense when they're ordered by atomic number, which means things that have similar properties can be grouped together. Now, like I said, only give yourself 2 marks for each section. You need to be smart when thinking about what the examiners are looking for. So these questions are really quite a long, complicated one. This could easily be divided into 2 6-mark questions. The first one being explain the reactivity in group 1. The second one being explain the reactivity in group 7. I can't explain why, but I really, really love this question because it really delves into your understanding of chemistry. If you can explain this and you understand it, you're going to be doing really, really well. And I'd expect you to be moving on to A-level chemistry and doing really well there. So you need to know that in group 1, the reactivity increases as we go down the group. I'm just going to divide this page in half, and I'm going to do group 1 over this side, and I'm going to do group 1 over as group 7 over this side. So in group 7, the reactivity increases as we go up the group. So you need to be able to recognise that every group 1 element wants to lose this electron. That is how they're going to get a full outer shell. So they want to lose the outer electron. And they're going to form +1 ions. So I've drawn you potassium and lithium here, and we can see that the distance from the positive nucleus out to this outermost electron here is much further in potassium than it is in lithium. And what the positive nucleus wants to do is to keep hold of that electron. But it's a lot easier for it to keep hold of it in lithium than it is in potassium, because there are shells in the way. So I'm going to do a bit of writing and come back to you in a second. So I've just explained that the further away an electron is from the positive nucleus, the more shells that are in the way, and the technical term for this is shielding. So the more shells there are, the further the electron is away, the more shielding that's going on. So the more shell, the less pull the positive nucleus has over this electron, so the easier it is to lose. The easier an electron is to lose, the more reactive it's going to be. So conversely, I'm now going to draw you some pictures for the group 7 elements and explain them to you in a second. So looking at group 7 elements, they want exactly the same things as group 1 elements. They want to have a full outer shell. And the easiest way they can do this is by gaining an electron in here. So what the positive nucleus needs to do is to pull an electron in. So they need to gain an electron, and they are going to form -1 ions. But exactly the same as the group 1, they have a different number of shells, and the shells are what affect the reactivity. So I'm going to do a bit more writing and come back to you in a second. So I've just written this down. So the more shells that are in the way, the more stuff that's in the way, or shielding being the technical term, of this positive nucleus reaching out and grabbing hold of an electron and pulling it in. The more shells that are in the way, the harder the nucleus is going to find to pull in a new electron. The harder to pull in a new electron, the less reactive it's going to be. Which is why things are at the bottom of group 7 are less reactive, and why things are at the bottom of group 1 are more reactive. So, mark scheme. Again, this is going to be a 6-mark written question. This is going to be a quality of written communication question, so don't do what I've done here and write short things in bullet points. Write it in full sentences, because that's going to get you the mark. Again, we need to be smart. I've asked you about 2 things for 6 marks, group 1 and group 7. So the maximum I want you to allow yourself for each is going to be 3 marks for group 1 and 3 marks for group 7. But this is how I would mark it. So I would give you a mark for saying that how the reactivity changes for each of them. I'll give you a mark combined for these 2 points, whether it gains or loses an electron, and what ions it forms, and then a mark each for explaining about the shielding, and then a mark each for the statements about what happens. So 8 in total, but only 3 per group. So again, this is a tricky question. If you came across this in an exam, they'd probably give you a bit more information, and they'd probably break it down a little bit, but there's no way you're going to do really well unless you're tested really hardly. So my aim here is to test you really hard. So you need to be able to recall that the Haber process is the reaction between ammonia, is a reaction between nitrogen and hydrogen, to produce ammonia, and this is a reversible reaction. We need to be able to balance this equation. You need to be able to remember that the commercial process is carried out at 450 degrees C, which is really quite a lot. It's carried out at 200 atmospheres pressure, and it has a catalyst involved in it. And something that they will probably tell you, but is always good to remember, that the forward reaction is exothermic, and the reverse reaction is endothermic. So it is always a touch weird that they carry this process out at high temperatures, but you need to be able to explain why they do. So in this question, I'm only asking about temperature and pressure. Again, when we're looking at 6-mark questions, we need to be smart. We need to be anticipating what the mark scheme looks like. So I want 3 points for temperature, and I want 3 points for pressure. I'll write this down and show it to you in just a second. So this is my answer here. I've divided it into temperature and pressure. And remember, I only want you to give yourself 3 marks maximum for temperature and 3 marks maximum for pressure. So the full reaction is exothermic, and it seems really counterintuitive that we would do this at a high temperature, because a high temperature would shift the equilibrium to the left-hand side. And I just want to highlight this phrase to you here, because this is a really, really good phrase, a really, really key phrase to remember and to write down your exam, but remember you have to apply it correctly. So a high temperature, you should remember this from C2, speeds up the rate of reaction. So this speed is going to, but a high temperature is going to speed up both the forward and the backward reaction. So 450 degrees is a compromise between favouring the reverse reaction and favouring a rate of reaction. Each of these bullet points give yourself a tick for, but remember only 3 ticks maximum. So when we're talking about pressure, I've written the equation out again for you here, and we'll notice on this side of the equation there are 4 moles of things, whereas on this side of the equation there are 2 moles of things. So when we're talking about gas, when we talk about particles making up space, this side of the equation actually takes up more space, and this side of the equation takes up less space. So a high pressure is going to forward the right hand side as it has fewer moles, and the equilibrium is going to shift to reduce the pressure. Again, each of these are going to be worth 1 mark, and your final mark is going to be for explaining how this is a compromise. So it's carried out at 200 atmospheres. If we carried this out at 10 times as much as 2000 atmospheres, the forward reaction would be a lot faster. But this will be quite dangerous for the people working there, because things that are at very, very high pressure are highly likely to explode. For example, if you squash a balloon and put the gas in the balloon under high pressure, it's much more likely to explode than if you don't squash it. So high pressures are very dangerous. They're also very, very expensive to build high pressure containers. If you have to spend hundreds of thousands, millions of pounds out on building a container to contain your really high pressure things, you have to think about the economics. Are you actually going to get that money back when you're producing ammonia? So I put this question in here because it's going to demonstrate quite a lot of skills going on. It's very unlikely they would ask you this sort of question in the exam, just because of the large number of skills you would have to demonstrate to do this. But I think it was a worthwhile question adding in here, because it's really, really going to test that you know what you're talking about. So ethyl ethanoate is an ester. To make an ester, we need an alcohol plus a carboxylic acid. And then you should be able to recognise that ethyl ethanoate is going to need ethanoic acid and ethanol. So using diagrams means I want you to have drawn me ethanoic acid and ethanol. So I just quickly sketch these out for you here. So the eth bit means that it is going to have 2 carbons in it, and each carbon, remember, is going to make 4 bonds with things. So a really good way to just check when you're drawing things out is, does everything have the correct number of bonds? If they don't, you've probably missed something, but it would be a very hard question that asked you to actually draw things. They're much more likely to ask you to identify things. I'm not sure why the reason behind this is, but organic chemistry has only recently been introduced to GCSE. It's much more common at A level. So this is the reaction. This is ethanoic acid. This is ethanol. And this is ethyl ethanoate. So we can tell this is ethanoic acid because of this group on here. Again, it has 2 carbons, so that's where the eth comes from. The ethanol, 2 carbons, and then this is the alkyl group here. Ethyl ethanoate. So we can divide this name in 2. The ethyl bit refers to the 2 carbons here, and the ethanoate refers to the 2 carbons here. And this bit in the middle is the functional group for an ester. These are the 3 functional groups that you need to know about for C3. If you can't find a functional group on the end, look in the middle, look for this functional group here, and chances are it's going to be an ester. So the way that I would have marked you for this would, I would have given you 1 mark for working out that we need an alcohol plus carboxylic acid to make an ester. I would have given you a 2nd mark for working out that everything needed 2 carbons. A 3rd mark for getting the correct functional group on your ethanoic acid. 4th mark for getting your correct functional group on your alcohol. 5th mark for getting your correct functional group on your ester. And then your 6 marks would come from saying that ethanoic acid plus ethanol makes ethyl ethanoate. So this question is asking about the advantages and disadvantages of adding chlorine and fluorine to our water supply. Again, this is going to be one that is going to have our quality of written communication mark. And this is, whenever I see an advantage or a disadvantages question, I think the easiest way to do this is to draw yourself a nice little table like this. So we can have chlorine up here, fluorine, and then the advantages and disadvantages. And it's a 6-mark question. I want to make sure we have at least 1 thing in each box so that we've made sure we've covered all the points, and then we need to add a few other things to make sure that we've made 6 points. Now, we need to be careful when we do this because this is a quality of written communication question. We are going to need to make sure we write in full sentences. So you can either do it in the table format to make sure you write in full sentences, or you can just write a list and make sure you cover the advantages and disadvantages of fluorine and chlorine. It's really, really important you do that. So I'll just write down my answer and get back to you in a second. So I've decided to use the table format because that's the way I like to do things, and I've written things quite briefly here. Remember, in your exam, if it's a quality of written communications question, write in full sentences, but there's absolutely no reason why you can't write in full sentences in a table. So you will notice I have at least one thing in each box, but there's a lot more to talk about chlorine fluorine, than there is about chlorine. That's absolutely fine, because it's a 6-mark question, it's not going to be an even division. So chlorine, an advantage is that it kills the bacteria in our water, but disadvantages is a possible cancer risk. Fluorine has lots of advantages. It prevents cavities, so our teeth health is improved. It protects our heart health, and it also builds strong bones. The disadvantages is that the government imposes this health benefit upon us, and we don't really get a choice, and there is also the possible cancer risk. I would just like to point out that the possible cancer risk is very, very slight, and you have to ingest massive amounts of tap water. to even be at the tiniest risk. It's not something you have to worry about. It's absolutely fine to keep drinking tap water, showering in tap water, brushing your teeth in tap water. It's just something you should be aware of purely for the purposes of the exam. You do not need to worry about it otherwise. So question number 10 looks quite simple, and the answer's quite simple, but there's a lot of learning that needs to go behind what goes on here. So first of all, you need to know about all the flame tests, and you need to know that let me just change the colour to make it a bit clearer. A lilac flame means lilac flames means that we have a potassium ion, and again, I said there's quite a lot of thinking that goes on behind this. You need to know that potassium ion is K+. So it burns lilac in flame and produces a yellow precipitate when mixed with dilute nitric acid and silver nitrate. So yellow, and this is a test for halide ions, and this is going to show that we have iodide present, and this is going to be an I- ion. So again, we need to bring in a few skills here. We have K+ ions and we have I- ions. We need to put them together so that, you know, the positive charges are equal to the negative charges. So this compound is going to be potassium iodide, which is going to be Ki. So quite a simple answer, but a lot of chemistry you need to know for that. So I'd give you 1 mark for saying that potassium ion has a lilac flame and then identifying the ion. I'll give you another mark for saying that yellow is a test of halide iodine, and that this shows that it's I-, and then I'd give you another mark for working out the formula of potassium iodide. And yeah, okay, I can only think of 5 marks for this, but again, there's a lot of chemistry that goes on behind there. You would have had to know all of the flame tests, and you would have had to know all the tests for positive and negative ions to be able to work that out. This sort of question is really quite common in C3. They really want you to do a lot more thinking than other things, and really actually working out what's going on. So this question looks quite simple, but it's really quite complicated. And that's the end. Really, really well done if you've made it this far. Every single one of those questions was an A-star question. So if you managed to do a couple of those perfectly, or if you've managed to get half the questions correct, then you've done absolutely fantastically. Please let me know in the comments if you have done this so I can congratulate you personally, but really, really well done if you have. If I was to set this as an exam set of exam questions in class, these are the grade boundaries that I'll be using to mark it. It's out of 60 or 59 rather, but it doesn't really make much difference. These are the percentages that I'll be using to grade it in class, but again, every single one of these questions was an A-star level question, so if you managed to do a few of them, absolutely fantastically well done. Thanks for watching. I really hope this is helpful. Subscribe so you don't miss any of my new videos. Share to help your friends get better grades. Any comments, corrections, questions or requests down below please.